This video is strictly for high-level IB chemistry students. If don't be scared by what this is, okay? The reason why you want to have a good look at this is this guy's actually found a way to quickly get lots and lots of data. And basically he's used a lot of mathematical derivations here. When it comes to high-level IB Chem, I'm sort of given up and thinking, well, I'm just teaching physics. And so when I see all these derived equations, I sort of like, yeah, okay, fine, we'll do physics and we'll just derive a stack of equations. And my big criticism of physics is as soon as they start to do that, there's endless numbers of assumptions that they're just ignoring and forget about. But this guy seems to be, this is a chemistry guy, so I think I trust chemistry teachers to teach physics more than physics teachers because he's given these assumptions here. Okay, fantastic. The problems with all these derived equations, the assumptions are that the mass loss due to the loss of water saturated oxygen bubbles is negligible. So he's saying that there's no oxygen coming off, and that the C is constant. Fine, that's the specific heat of water. No heat is generated by the stirring. Well, that's not going to happen anyway. And the reaction under the conditions employed is adiabatic. So I looked that up. That means that there's no heat going in or out of the system. No heat going in and out of the system. So it's not just a closed system. He's saying it's an isolated system, which is just impossible. But I guess if you're using a calorimeter, that's possible. But as you can see, I'll show you the experiment soon, it's really, really bad. It's not just not an isolated system. It's not just a closed system. It's a completely open system. And there is huge amounts of oxygen coming off, carrying away heat. And it gets so warm that there's steam going off. And this is like going on for like half the experiment. And even when the experiment's going, the cooling's so dramatic that it drops in temperature while the experiment hasn't even finished. So there's massive errors in this, but I'm going on with this. I still think this is highly valuable because that's just for this experiment. You could fix all that by making an experiment that doesn't give off, using an experiment that does not give off gases. So that's the huge fault with this one. But everything else is quite good. First of all, spend an hour struggling with this. You have to be happy with the mathematical derivations. And I struggled with that for at least an hour before I thought, yeah, okay, that all looks fine. And I'm happy to work with that. And so if I'm just going to look at this, you need to go through each reaction. So excuse me, and we're going to have to do that. I know this is going to take a long time. So the first one is the rate of decomposition here equals the rate of temperature increase. And if you look at those values, this is Q, so this is MC delta T. I've written it kind of strange. But if you want to confirm with the units, that's in joules, although it's kilojoules if we're doing kilograms here. So that could have been an error there in the calculations. Or I could make an error somewhere else. So if I've got a problem, I'll come back to here. There's a few other things that I'm not 100% sure of, and if it didn't work out, I would come back and reinvestigate those. And then this should intuitively make sense. So the rate of reaction, that's changing in concentration. So the amount of volume matters, and the enthalpy of the reaction is going to affect how much heat's given off. So that should equal. So how quickly it is how much temperature it should rise, and using the various equations. I thought that through in my head for quite a while and was okay with that. This one here is just now playing around with that. So it's good to jump to our end product. Now, hopefully you've done the lesson. So you know that to work out the activation energy, we're going to use an Arrhenius plot. And so if I just, if the Arrhenius plot will be 1 over T, and we need the rate constant. So the T is easy because we're going to do temperature here, and somehow we need to get this to be a rate constant. So that's our end game, and once we can get that, we'll get this and we can do the EA. I'll show you the calculations at the end after I show you the experiment. So we need to get K, basically. That's the difficult bit. And so you can see that K is here, and we're just rearranging all the equations to get a K. And so we're just manipulating this for a rate. And why? We're doing that, so this rate here, so that we can substitute in the rate equation. So the rate equation for this is given somewhere in this article here. So there's the rate constants, what we're looking for. It's affected by temperature, the concentration of the reactant, and the concentration of catalyst. And so we can use that equation to get a K into the system now. So we've got substitution here. This is probably going a little too fast because it did take me a long time to be happy with all of those things. This one here, so the final minus initial temperature is the total temperature change. And then if you take minus the temperature at a certain point in time, you're getting some sort of percent stage. So if it's like half the temperature until final, then you're going to think, well, it's half finished and half used. And so that's how we get some idea of where the reaction is concentration-wise. And so that's the initial concentration and the final, well, the concentration at point T. So it'll be the initial concentration times a certain percentage completion, and that'll give you the concentration we're looking for. All right. And so the rates here, so this one here, the slope here is the instantaneous rate, which is over here. Okay, I'll show you how to do that with the calculations later. And so what we have here is just more substituting here. That's the final achievement there. And those things are basically substituting. So we're substituting from equation 4, from equation 5, substituting and rearranging this still until we finally get the slope. We get this equation here so we can get the K. So it is very tricky. And I hope hopefully those little red boxes will clear things up for you. But you need to be okay with everything that's going on there before you move on. All right. Okay, so just so I don't have to come back to this document again, just a side note. So my reaction was far less steep. So these guys went up to 90 after 600 seconds. So we'll just remember that. It was a nice experiment as far as it was really easy to set up. It's really easy to make 12%, 30 mils of 12%. I just added I think it was 40 and 60, 40 mils of 30% to 60 mils of water, and this was 1.66 grams in 10 mils, and then I just took half a mil with a partial pipette. So I'm just trying to see whether it works out. They're not huge errors, even though I didn't do that too precisely. Okay, and the answer we're trying to get is 56, which is the amount of activation energy it requires. So I start off here with just getting the temperature stable. So I put the hydrogen peroxide, came out of the fridge, I let it sit for a while. It's about 20 degrees in the room. And then I put half a mil of that 1 mole of potassium iodide in there and gave it a quick mix. And then we're off. And I'd set the temperature for every 10 seconds. I think that's even greater, longer time for the research article. All right, now this takes 20 minutes. And so I'm going to have to jump around a bit because I'm not going to show the whole 20 minutes. But basically you can see, I'll just jump around to various sections. I'll just cut in and out. I think I'll jump. So you can see in real time how profusely it really bubbles. And it bubbles with even steam coming off. And even when it drops, it's still reacting quite vigorously because the rate of cooling is quite extreme. So as you get up to the 60 or 70, it cools off so rapidly that even when it's dropping, it's still actually reacting. And even when it starts to slow, you can still see fine bubbles coming off. So I just give up after 20 minutes and never really finishes. And the rate of cooling is really, really quite slow. So there's a huge error. And as I said before, their gradient is much, much steeper than mine. I had massive cooling effects because of all the loss of hot oxygen gas just constantly coming off, it being warm itself, so steam coming off. So all of those assumptions are terrible, and that shows up in the data. And so then now that I've finished, I just grab this function here to get the gradient, and you might not get enough decimal places. So I'm just showing you, just go to experiment tools, calculated data, and then you just play around with these digits here. So that's just a technical detail on how to get the gradient to enough decimal places. And so I just moved it up and down and got values. So what I did was I moved it up. These temperatures, 21, 27, 34, 44, are up like 100, 200, 300, 400 seconds. But once you got too high, there was that massive cooling effect that stuffed everything up. So I couldn't really go above 50. And so I only took those 4 values. And so I'll upload these resources so you can just take this exact sheet, so you can not stress too much about all these little things. So that algorithm there, that's not too bad. The gradient I read off, that's from the those values are taken from the graph, so you can read it off that article, which I'll have there, so you know that's the initial and max. This one here is you'll see that from the formulas in the research article, and that's the formula to do a negative a log to the natural n. Okay, and so that's how. So then I just graphed this. So I just grabbed this and hold down the control key and this one to graph it. Cleaned it up a little bit, put that in there, and so that's the Arrhenius equation. And so it's 1 over t down here. So the gradient, so EA equals, so M equals negative EA over t. So rearrange that. The activation energy is M times R. So there's the values in there. And so that works out to about 10 kilojoules per mole. And so that's the answer. So does that make sense? If you look at the article, you'll see that their curve is actually much, much steeper, even though I'm using different increments, so it doesn't look any steeper. It looks exactly the same. And so their gradients are much, much steeper. And that would mean that results in this line here becoming much, much steeper. And so this number is much, much larger. And that makes sense because the steeper the gradient on this Arrhenius curve graph thing here, the higher their activation energy. And I got a far less gradient, and so my activation energy is only 10 instead of like 50 kilojoules per mole. And so it seemed like there wasn't a lot because of all that heat loss. That gave me the much lower result. So it's a pretty simple experiment, very quick and easy. Like it a lot. Definitely think this is the way to go. I think that particular experiment loses so much heat it's not funny, and so there's at least he put the assumptions in there and he did get a good result. I'm not quite sure how he avoided all the heat loss. So fantastic experiment. Do it with something else that's not going to have so many violations of the assumptions.